Hello, this is the first video for section 10.3, which is about polar coordinates. If you'll remember, the last thing that we learned about before spring break was parametric equations and parametric coordinates, and that was section 10.2. So 10.3 is yet another type of coordinate system that allows us to easily graph different curves that use especially trigonometric functions. So what is a polar coordinate system? Well, you already know about a Cartesian coordinate system. That's the system that you're used to with X's and Y's. And then of course, before spring break, we learned about the parametric coordinate system, where there is the introduction of a parameter t and two equations, X and Y, for each curve. So here we're learning about the polar coordinate system, of course introduced by Newton, which is convenient for a lot of different reasons. The way this coordinate system is drawn is an origin, which we call the pole, which of course is where the word polar comes from. The pole is the origin, and we label it as an O. And then we draw a ray, which of course is a half line, starting at O, called the polar axis, which is what you see here in figure 1. So you can sort of think of that as the x-axis, which is why it's labeled that way, but that's the polar axis. And then r is named r due to the fact that in general, we consider r to be the radius of a circle. So a point in a polar coordinate system consists of two pieces, just like in the Cartesian coordinate system, an r and a theta, where the r represents the length of the line segment to get out to the point P, and theta represents the angle at which you draw the line that gets out to the point P. So what you see on the screen here is a theta, an angle in radians, and an r, a radius. And if you move to that angle theta and go out r units, you will arrive at your point P, which is represented with r and theta. Those two together, again, are called polar coordinates. We use the normal convention of the angle moving counterclockwise around the x-axis or the polar axis. And then if the angle is negative, we move clockwise, just like what you're already used to for trigonometry. If P is 0 and R is 0, then that would be considered the origin, again, which is called the pole here, no matter what. So what if R is negative? So when R is positive, we have an angle theta and an R, a positive R that goes out to reach the point P. If R is negative, it is on the same line, but in the exact opposite direction, which makes the theta look different, and it is by a factor of pi. Theta plus pi is your new angle, and then R gets you out to the point negative R theta. So again, it looks completely different, but the way you deal with a negative R value is by simply going the other direction on the line segment that you would have gone if R was positive. So to recap that, if R is positive, then the point R theta lies in the same quadrant as theta. Remember, quadrants 1, 2, 3, and 4 around the coordinate system in a counterclockwise direction. If R is negative, it's going to lie in the opposite quadrant of where it would have lied if R was positive. So as a reminder from the previous picture, what you see here, negative R theta is the same as the point R theta plus pi. So let's see a couple of examples of how you plot points in the polar coordinate system. So in part A, we have the point 1 and 5 pi over 4. So here R is 1, and theta, the angle, is 5 pi over 4. I know a lot of you probably think a little bit more clearly in degrees, so if that helps you to convert these angles to degrees, that's fine, but know that the accepted convention for polar coordinates is always radians. So in order to plot this point, you would start by finding where is the angle. So you can see down here at the bottom, where is 5 pi over 4? and the blue line is drawn to where that angle gets you to. Remember, pi over 4 is the same thing as 45 degrees, if that helps you figure out where the angles are. And then once you've found the angle, you use r to determine where the point will end up. So we have our angle determined, and then we go 1 unit out on that line segment to find our point 1, 5 pi over 4. In part B, our r is 2 and our theta is 3 pi. So again, we start with finding where is 3 pi. Well, we know 2 pi is all the way around a circle 1 time, and then 1 pi more would get us over 180 degrees on the other side of the x-axis. So then to find the final point, we simply move out 2 units, and then we have 2, 3 pi as our point. In part C, our r is 2 and our theta is negative 2 pi over 3. So we start by finding where is negative 2 pi over 3. Now, since it's negative, we're going in the clockwise direction instead of the standard counterclockwise direction. So we have negative 2 pi over 3 gets us to our line segment, and then we go out a distance of 2 units to get our final point, 2, negative 2 pi over 3. And then in the last example, we have an r of negative 3 and a theta of 3 pi over 4. So we start by finding our angle, 3 pi over 4, and then since r is negative, instead of going out on this ray, we go in the exact opposite direction 3 units, and to find our final point, negative 3, 3 pi over 4. Now notice, in that example, let me go back one. In that example, if I gave you this point and didn't tell you the coordinates, negative 3, 3 pi over 4 might not have been your first guess. You might have chosen a different angle with a positive r instead. And that's what's sort of unique about the polar coordinate system, is you can have more than one point represent the same exact location in the coordinate system. And that is what this screen is, or this slide is explaining. In Cartesian coordinate system, every point only has one representation, but in the polar coordinate system, you can have infinite representations for the same exact point on the system. Now, this is the generic version. A point r, theta, can be represented by an infinite number of representations as written here. So if you go multiples of 2 pi away from theta, you will always end up at the same angle. Hopefully that sounds a little bit familiar from trigonometry. And then for the second point, that same exact angle could also be represented with a negative r instead of a positive r, with a different multiple of pi, as we saw in this example here. When r is positive, we go out on the ray, and if you go the opposite direction on that same ray, that would be like adding pi to your angle, because we're going 180 degrees in the other direction. Okay, so how do we connect polar coordinates with Cartesian coordinates? This is what this picture is trying to show us. So in the polar coordinate system, we have an angle theta and a distance r to get us out to the point P. Well, if we plot that same P on a Cartesian coordinate system where we have X and Y, you can see that we should be able to represent a point r theta by a point X, Y. And how do we do that? We go back to trigonometry and use triangles. So on our triangle, you can see that we have all 3 sides of a triangle labeled, and we have an angle theta. So if I wanted to know what r was, wrong way, sorry. If I wanted to know what X and Y were, I know that the cosine of theta could be represented by X divided by r, and the sine of theta could be represented by Y over r. And that is what is written here. Cosine is X over r, and sine is Y over r. So if I solve both of these equations for X and Y, I would get X equals r cosine theta and Y equals r sine theta. And therefore, if you know the coordinates r and theta, you can figure out what the corresponding X and Y coordinates would be. And that is what this is showing. Now, what if we want to go the other way around and we have the Cartesian coordinate system points, but we want to know what that would be on the polar coordinate system, r and theta? Well, if you think back to circles, if r is the radius of a circle, then x squared plus y squared equals r squared due to Pythagorean's theorem on the triangle. And the tangent of theta would be y over x. Why are we using tangent? Because we're assuming we only know x and y. So since we don't know r yet, we aren't going to use it to find theta. And if we know the tangent of theta is y over x, then of course we can use a inverse function to find theta itself. So in our next example, let's convert a polar point into an xy point, Cartesian coordinates. So we have r is 2 and theta is pi over 3. So if we use our equations, r cosine theta and r sine theta, simply substituting in r and theta, we end up with x is 1 and y is square root over 3. And remember, you can always use your calculator if you don't remember the basic the trig functions for the basic angles. I know that pi over 3 and pi over 6 sometimes get a little confusing. So don't be afraid to use what you have at your disposal. So what this means is that the polar point 2 pi over 3 is the same point as 1 square root 3 in Cartesian coordinates. Now let's go the other way around. Let's say I have the Cartesian coordinates 1, negative 1, and I want to know how that translates into an r and a theta. Okay, so if we choose r to be positive, which is usually preferred, then using our equation with Pythagorean's theorem of r squared equals x squared plus y squared, we can plug in x and y, and we end up with r equals square root 2. And then remember, tangent is y over x, so that is negative 1 divided by 1, which is just negative 1. Now, the point 1, negative 1 in Cartesian coordinates lies in the fourth quadrant, so we have to make sure that our final answer with r and theta also is in the fourth quadrant, because remember, we're trying to find the same exact point. So we need to know, when is tangent negative 1? Well, that can happen at negative pi over 4 or 7 pi over 4. Again, you can use your calculator to help you with this, or your knowledge of the unit circle. So we have a couple of different options, because remember, there's technically an infinite number of points for polar coordinates. So we can say square root of 2 negative pi over 4. We could also say square root 2 7 pi over 4. Both of those are in the fourth quadrant and represent the same exact point. So we'll stop there for now for the first video. Thank you for listening.